Now, while bounded minimax helps avoid some wasted work, we can do even better. Consider the game tree shown here. In this case, unlike the earlier examples, there are many terminal nodes that are neither 0 or 100. In determining the maximum score for the top node of this tree, a minimax player, even a bounded minimax player, would examine the entire tree. However, not all of this work is necessary. So as an example, consider the fourth terminal node on the lower left. Even before that node is examined, the player knows that his opponent can keep it to at most 10 points. And on that branch, based on the third node, it already has a move of its own that gets it 11 points. Exploring the fourth node can only decrease the min node's score, and the player is not going to choose it anyway, since it can get 11 points somewhere else. So there's no point in examining it. In this case, the saving is only one node. But in other cases, it can allow a player to prune whole subtrees, as we'll see in just a bit. Alpha-beta search is a variation of bounded minimax that eliminates such wasted work by computing bounds dynamically and passing them along as parameters. One bound, called alpha, is the best score the player has seen thus far. Another bound, called beta, is the worst score the player has seen. In examining new nodes, alpha-beta search uses these bounds to decide whether to look at further nodes. If the partial result at a min node is less than alpha, then there's no point in examining any other descendants of that node, since it could only decrease its value, and the player would not take that choice given that it has a higher value elsewhere. And analogously, if the partial result at a max node is greater than beta, then there's no point in considering other options, since that can only increase the score, and the player's opponent would not allow that, since they know that they can keep the value to no more than beta. So here's an implementation of max score and min score for an alpha-beta player. In computing the max score of a max node, the player takes the maximum of alpha and the min score of the node obtained by performing any legal action in the corresponding state. And symmetrically, to compute the min score of a node, the player takes the minimum of beta and the max score of the node for the state obtained by executing the joint move for any legal action. Now let's apply this procedure to the tree shown earlier with initial values 0 and 100 for alpha and beta. In the tree shown here, we have written in the values produced by the alpha-beta procedure in this case, and we left the other nodes blank. So as you can see, we pruned away that fourth node at the bottom of the tree, but we also pruned away quite a few others. It's just not an insubstantial savings. In this particular case, it was modest. However, in general, alpha-beta search can save a significant amount of work over full minimax. In fact, in the best case, given a tree with branching factor B and depth D, alpha-beta search needs to examine at most order of B to the D over 2 nodes to find the maximum score instead of order of B to the D. This means that an alpha-beta player can look ahead twice as far as a minimax player in the same amount of time. Or looked at another way, the effective branching factor in this game is the square root of B instead of B. It would be the equivalent of searching a tree with just 5 moves instead of 25 moves.